equal to 0 and this is less than equals to 2x, worst case scenario, rho of 2x plus x squared, right? So, yeah. So this is also modulus of continuity, so that's yeah, so this is kind of a clever idea. I think it's sort of useful. I haven't used it, but I think it's useful. Okay, so yes, I didn't do the other way around. You know, you also can do something touching from below. So yes, we really have ux0 plus h of x0 du x0 equal to 0 in the common sense. So not in the tricky sense of viscosity solution, but in the common sense, in the correct equality. So yes, so that means U is a solution in the almost everywhere sense. Okay, so that makes sense. Okay, okay, maybe I should say one thing. This is a very tricky business actually. It's sort of like okay, remark. This is one of the points that people sleep under the carpet because it's just too hard. So that's why people sleep it under the carpet. Okay, now look back at the. Let's look back at the vanishing viscosity method. This is vanishing viscosity. By the way, tomorrow I will prove that actually U is just easy, but under some conditions. Vanishing viscosity. Okay? So the question is this is just what happened at S epsilon goes to 0. So we proved that we have a priori estimate. That we do have, actually in this case, U epsilon plus the gradient, less than equal to 0, and then by Ascoli, and then my uniqueness result actually, but we have U epsilon, because by Ascoli we all have conversion along subsequence. But the limit is unique, so by Ascoli and uniqueness result, we have conversion along all sequence. This is sort of tricky. Ascoli is a stock tool, so you need to converge along subsequence. But here the limit is U plus h of x du is equal to 0. This is unique. So any subsequent going to converge to that, so conversion along full sequence. You have some conversion U locally, and informally. And also we're going to have that at U is both the viscosity solution and you see I'm being careful. The viscosity solution means it's unique, but a distributional solution. Wow. A solution almost everywhere. I'm going to be careful.
Subsequence of U epsilon V epsilon.
Yeah, that's a good point. So via subsequence, I will have as a last goal, you're going to give me conversion along subsequence, right? But the limit is unique. So any subsequent is going to converge to that. So that means all of the sequence converge to that. You can prove it by contradiction. Assume not that I have a subsequent converge to a different guy, which is a contradiction. Right? So assume not.
What if it doesn't converge?
Huh?
What if it doesn't converge?
It converges to a different limit. So assume. Okay. This is a very tricky point.
It blows up.
There is a subsequence that we converge.
No, it cannot blow up because of the a priori estimate. Yeah. So this is a very tricky point. There are problems we are looking at now. There are some very important questions that we have convergent along subsequence, but not along sequence, full sequence. It's sort of like blowing up limit sometimes can be different. Or like in curvature flow, I think Tobias Coding and Nicosi are looking on that. In order to prove everything converges in a full sequence, sometimes not. To have a blowing up a little. But here I use this result. We have this with only as fully conversion along subsequence. It's not easy. And here is both a viscosity solution and a solution almost everywhere. But you see the device we use to prove that it's a solution almost everywhere is weird. It's not coming from the PDE. It's coming from a different device that you define sort of cool test functions. So now going back here, what are we doing? We have conversion for U epsilon to U. Here, of course, we have not this solely PDE in the everywhere sense. And in order to prove a solution almost everywhere, we go into a different way. So that means actually we don't see anything. So question, what is the relation of du epsilon and du? Well, of course, by subsequence, by passing through subsequent, you have du epsilon j converse quickly starting L infinity to du. But do we have strong conversion, or we have any other sense? If we have strong conversion in L something, some other sense, we do have this a solution in almost everywhere sense right away. But that's a very big question that still remains open. And then we don't know. We don't know that du epsilon j converges to du in some space or in some space. And if you don't know the structure so this is a very important fact that, for viscosity solution is very nice, it's very clever. It's, we basically bypass the difficulty of not understanding the structure of the gradient, the Hessian, and Heidegger sort of crazy things. We bypass it because we only consider conversion at the U level. It's very clever. We don't see any breakthrough of the gradient, we don't see any problem with the regularity. So that's why the theory has been very famous because it's standard, it's quite easy to use. It's sort of like if you always stop at one closeness, come on. You have the machinery. So over the last 30 years, most of the time it's stopped at one closeness. The deep question about higher regularity, or let's say the deep question about understanding U intuitively is still left pretty much over. That's some progress. We're using this device kind of posterior in some sense, kind of like that it is designed, but you don't see any structure of the gradient. You just look at the test function. So no structure is being studied. And even if it is being studied, most of the time it's for convex case. Okay. So that's the end of kind of the theory of the three big questions. Okay, now I need to convince you that, okay, now you have a good thing, you have fun, but you need to make sense of it kind of correct. Okay, so now connections to Hamiltonian, Lagrangian, Hamiltonian. Well, I'm going to switch to Lagrangian viewpoint. Lagrangian viewpoint. Optimal control. And differential gain. So I'm going to switch to a completely different thing. And I'm going to show that actually from all those viewpoints, we're going to get this solution. So that means the thing we consider as sort of natural. It's kind of the thing we expect. What do we mean by Hamiltonian Lagrangian viewpoint? Because it's Hamilton, there's Hamilton there. So Hamiltonian. So let me give you one example, the classical example in classical mechanics. So Hamiltonian is total energy is kinetic energy plus potential energy. So this is kinetic energy. This is potential energy. And then we have the Lagrangian Lx cubed. It's a Lagrangian. It's often denoted as L is the H star, which is the Legendre transform. Of H. So what do I mean by Legendre transform? So the definition is the following. Lx cubed is the supremum of O over P in Rn of P dot Q minus H of x cubed. So that's the definition of Lx cubed. This is kind of weird, bear with that. So now let's compute it for this case of classical mechanics, Hamiltonian. Let's do computation. Yes? You can ask a question. Yes? So let me do the computation for that classical mechanics. So if I plug that in, Lx cubed is supremum of P dot Q minus, I have that explicit Hamiltonian, minus 1/2 P squared minus V of x. Okay. This, the sum of this appear, I think, when P is equal to 1/2 Q. 1/2. P is 1/2 Q.